We have two ways to come up with this strategies. One is this Nash equilibrium, other is von Neumann strategies, let's say. No surprise, they are supposed to be the same. A Nash equilibrium is a minimax solution, a minimax solution is a Nash equilibrium. So, this direction we will do okay. Sounds good? Not difficult. You already see kind of equivalence, and even this direction we have kind of already done. This is the proof, right? Because y naught is the one minimizing this. If my strategy is fixed at x naught, there is no incentive to change y for Bob, right? The entire proof was this exactly. It is saying that y naught minimizes this quantity. Right? So let me just write it. Since y naught minimizes, notice this is much simpler now, right? This is x naught is fixed now. The only variable is y, right? So if Ellis's strategy is fixed, I am trying to find out what minimizes this, and I figured out it has to be y naught. Minimizes Bob change strategy. Bob is already at the best possible strategy for x naught, right? And the same thing you can do for Ellis. You fix y naught, Bob's strategy is fixed. There is no point for Ellis to change x because she is already getting the maximum payoff. She is getting x naught transpose a y naught, which is Bob plays y naught, Ellis gets x naught transpose a y naught, which is right. And again, same reason, x naught maximizes this thing when I fix y naught. Okay. So that means, why would Ellis change x naught to something else? She's already at the maximum payoff. Okay? No, but I will only change if I get a better payoff. Equal payoff, there is no point to change. Okay, good. So, any exists is equivalent to now showing the Minimax theorem. Do you see this now? Right? If von Neumann's Minimax theorem is true, this min-max is equal to maximin. That means there exists x naught and y naught, so the payoff is x naught transpose a y naught, and we know x naught y naught is a Nash equilibrium. So if I show von Neumann's Minimax theorem, then I have shown existence of Nash equilibrium. This is our task now, to prove Minimax theorem. and if the time was 3:15, I would have written strong duality and gone home. But I have 15 minutes, you are lucky, so I will say more. Okay? Yes, this is going to be a strong duality. That means this is going to be a primal problem, this is going to be the dual of it. Okay, this is the idea. If someone tells you the idea, what is going to be your objection? Why, if someone gives you this much idea, why should you not be happy? First thing. If you're happy, then we can go home. Why should you be not happy if someone just tells you, oh, this is strong duality, this is an LP, the dual of it is this an LP. What is the first thing which comes out, sticks out? This is not linear. What are the variables here? X and Y. Right? This is Aij, Xi, Yj. This is not linear. So, the idea is great, but is not linear. Okay? Clear? So first thing is to convert it into a linear program. So the proof of von Neumann's Minimax theorem, the proof is basically how to view this as a linear program. This is an exercise in converting this problem into a linear program. Okay? Good. Let's convert. We have no other option. This is what Alice wants to do, right? Now, let's say Alice's strategy is fixed. Okay? So, suppose X is Alice's strategy, right? And suppose Bob knows about X, right? How will you calculate Y? It's much more simple than that. Forget about linear program. How will you, if you knew X? Okay, so you are thinking of as a linear programmer or whatever, maximize this, minimize that. I'm thinking of like if you give it to your younger brother or sister, right? What will be? They will say, oh, X transpose. What if I play strategy 1? What if I play strategy 2? Right? What is the pay? Huh? Right? But this is the start, right? I'm saying this is the thought process. What if I play 1? I will come to the mixed strategies later, but 1, 2, right? So 1 will have some payoff P1 or P1. 2 will have some payoff P2. How many strategies are there for Bob? N. Pn. Right? One obvious thing was to O, which has the minimum, smallest payoff. But now we are allowed for mixed strategies, so I can say yeah, mu I, yes. Probability distribution. Arey, forget about linear programming for a few minutes. Forget about linear programming. Summation. Okay, let me tell you another problem. Right, we are all motivated by crimes. Suppose you are a thief. No. Suppose you are a thief. Okay. Unfortunately, you are a lazy thief. So you only have a 1 kg bag. You go to a house, the house has silver, gold, bronze. Right? Because again, as a thief, if you go to a house, you can take 1 kg of a combination of metals. You have silver, gold, silver, bronze. What will you do? You will put all the gold in your bag. Why would you put silver? Why do you take silver or bronze, right? assuming gold is more expensive than silver, more expensive than bronze. Sometimes silver is more expensive. Okay. I thought you knew that, no? Swarn Padak, Rajat Padak, Kansya Padak. No? Okay, anyway. Right? So what will you do? You will take 1 kg of gold, obviously, right? So now here, you can take P1 with some, P2 with some probability, Pn with some probability. You want to maximize, minimize, take the minimum thing here and just put all your weight there. You see it? Yes? What is the other way to say it?
So we have the max of PI, right?
Yes.
Oh yeah.
Yes. The other way to say it this is minimum or a maximum for a linear program lies at a vertex. One comma 0 0 0 0 0 1 comma 0 0 0. What is this? Your feasible region. It is this simplex of 1 0 0 0 0 0 1 0 0 0 0. You are optimizing a linear probe over it. The maximum will lie at a vertex. So I hope now you are convinced that this is true. And this is the essential part. Once you see this, then it's easy. Okay, so now let's convert it into a linear program. I shouldn't erase this, no? Okay. So rest of the proof in this much space. Okay, so then whatever is the payoff, right? The payoff would be A star I or AI star? This is the column, right? It's the column of, no, row. Right? Okay. How do I write it as a linear program now? So let me just see this, always is less than equal to, greater than equal to. Sorry. Maximize the payoff such that okay, for all I. Okay, I think this is, this has to be star I. In this case, Bob's strategy is fixed. Sorry, Alice has a Bob. Yeah, Bob's strategy is fixed, right? And that payoff is given by a column. I is Bob's strategy, right? And second place, right? That means the payoffs are given in the column. It's a star I, right? So do you see that these programs are equal? Since I want to maximize lambda, lambda has no other constraint. So it is going to be the minimum over all these quantities. Clear? Once more, why are these two programs equal? Lambda, if you want to maximize lambda and you have these constraints, how will you put lambda? You will take the minimum over all these quantities and put the maximum possible. Lambda is less than 2, lambda is less than 3, lambda is less than 4. Maximum lambda. What is lambda? 2. Right? So these two things are equal. right? Because again, this implies pick lambda to be min over I. A star I. Okay, great. Now what to do? Now you should know what to do. Yes, whenever you see a linear program, take the dual. And once again, now if you can directly take the dual, it will be helpful instead of converting into a standard form and then taking the dual. So, U is the multiplier here. Y's are the multiplier here, right? What is the number of Y's? Number of columns in A. Match, right? U. Now, if you sum up for lambda, you will get summation yi equal to 1. The constraint corresponding to lambda, remember lambda is a variable here, right? So for lambda variable, when you look at the constraint, it will say, see, there is no lambda here for u. So u is out the picture. It says summation yi equal to 1, right? You can match up everything. This is less than equal to, that means y has to be greater than equal to 0. This is equal, that means u is unconstrained. We have seen this multiple times, right? Less than equal to, we can check the sign by the meta inequality, right? Equal means the corresponding constraint is, this again is of the same form. This is what we have done. A transpose y, x, ax, right? So this changes to this, right? Do you want to take the dual yourself, or you trust me? If you have to take the dual by yourself and trust me, then you will obviously trust me, right? If the choice was just trust me or not, then probably you don't trust me. If I was taking the dual, but again, whenever you have to take the dual, remember, write the variables, create the constraints corresponding to each variable here. Again, the constraint here does not give you the constraint in there. The summation yi is coming because the lambda, the coefficient, this is not just one equation. These are n equations. Each of the equation has coefficient 1. That is why you are getting summation yi, right? Stop matching constraint to constraint. Constraint here corresponds to a variable there. And with that, you can match up everything. Okay? And now you should be excited. Because what is this? Right? No, I is varying, right? Summation over I. Yeah, this is the jth, right? This is the row, right? I have to, Bob's strategy is fixed. Alice's, Alice's responses to Bob's chth thing, right? So this is, no, I'm probably saying the opposite way, but will work out. Okay, right? So then, again, this I can replace by this. Oh, you are right. This has to be J star. So this is J. Thank you. Right? So this is equal to this because the thief is smart. He or she is going to put all the gold in the bucket. Right? There is no point having a mixed strategy when y is fixed. If you fix y, the best response here is the deterministic strategy which maximizes this. If there are multiple deterministic strategies which maximize this, any linear combination is also okay. Sounds good? Okay. So yes. So then, by strong duality, so for a two-player zero-sum game, this maximin is equal to minimax. The optimal solutions give us the Nash equilibrium. So this also tells us how to compute Nash equilibrium. Because this is a linear program, we can apply our solutions to this. Okay? Thank you.